Swayam Prabha. Digital India. Educated India.
Resume our discussions on the variational formulation that we have started in our previous lecture. So, today what we are going to look at is the transverse vibrations of a hanging chain. So, this is a chain, as you can see, this is an inextensible continuum. So, we are going to look at the equation of motion of such a chain. So, let us consider this chain hanging in a uniform gravitational field So, we assume that this chain is made of a material of density rho, has a constant area of cross section A, has a length L. Now, this is an inextensible chain. So, though it does not in a way resemble a string in that sense, which is an elastic continuum, one dimensional elastic continuum, this is inextensible. Yet, as we will see very soon, the equation of motion, at least up to the linear order, is similar to that of a string. So, we are going to write down the energy expressions. So, the kinetic energy. So, at any location x, our field variable is w x comma t. So, the kinetic energy of an infinitesimal element can be written as half rho a dx is the mass of the infinitesimal element, and velocity square. So, if I integrate this over the length of the string, then what I have, this is the kinetic energy. Now, the potential energy. Now, the potential energy of this chain. Now, why this chain restores back to its vertical position? It is because as it deflects or as it is disturbed, the potential energy of the chain changes. So, it increases. Now, to calculate that, let us look at a small element of this chain. So, this is the undeformed configuration of the chain, and this is the deflected configuration. So, this infinitesimal element had a length dx. Now, since this chain is inextensible as we have assumed, so the length of this infinitesimal element in the undeflected or in the equilibrium configuration is same as in the deflected configuration. So, this is also dx, but now this is deflected. So, I will represent it as a vector whose length or whose magnitude is dx, and these vectors I will represent as this way, and this vector at x plus dx is given by this vector. So, if you write out this vector equation, so we can represent this ds vector in terms of the deflection of the chain. Now, if you take the magnitude of the vectors on both sides, then as I mentioned that the magnitude of this is still dx because the chain is inextensible. So, what I will do is I will take the magnitude square, let us say, and if you simplify the right hand side, we have this expression